Alright, I'm going to talk about derivatives, gradients, instantaneous slope, or whatever you want to call that. And for that, I have three mountains, three functions actually. This one goes like so. The second one is the Everest. And the third one maybe falls like that. I will call this to be my x direction, the horizontal distance. And this one defines the height of all these mountains, y of x. And what I am looking for is, as I track on these mountains, I want to know how quickly I am climbing up as I move in the x direction, or maybe how slowly I am coming down as I move ahead. That's what I want to know. I want to know how fast the height is changing with x. And I hope you can guess it already. You will climb faster on the Everest as you move in the x direction, as you make a side step in the x direction. And it's easy to show. Suppose you are here and you make a side step, delta x, then you will rise up to a higher altitude by a height of delta y, right? That's the cause and that's its effect. And if you had made the same side step here on this mountain, you will see you didn't climb up much. Maybe you climbed this much, delta y. And it's very clear, delta y on the Everest is larger than what you can have here for the same side steps, for the same delta axis. And so we say delta y, the change in height for the Everest is rapid compared with that one. And so this ratio tells you you will climb faster on the Everest. And you could do the same here, but instead of rising up, you are coming down, delta y. And since you are coming down, you would expect negative signs for the delta y. And that's the whole idea about derivatives. You want to know how fast, or maybe how slowly, things are changing with movement or maybe with time. You might want to know how fast the temperature is dropping in this room as you move from here to that corner. Or you could ask how fast the temperature is changing at this location with time when you move from morning to noon. So you might want to know that. Oh, by the way, you didn't have to compare these three mountains to run this whole argument. I could have done everything on this mountain, and I'm going to do that because I need one or two things to tell. So this was your x, and this is your h of x or y of x. It's alright, man. It was going like that. And now I could ask you how fast I am climbing here, here, and there. You make a side step, right? Make a side step, a little one. Make one here, one there, and so delta x, all of these are the same delta x's. Then you will find delta y here is larger than what you can have here. Look at here, you are climbing barely here. And so we say, since this ratio is going to be larger around those points, we say the changes are rapid there. So we say the derivatives are going to be larger around those points compared to that location. Right? And what is delta y here? Well, that's a flat surface. You make a side step in the x direction. You're not rising up, you're not coming down. So delta y here is 0. And so derivatives around those points will be 0 because we are interested in changes, right? And there, no changes are happening. Height is not changing. You're not climbing up, not coming down. So derivatives, they're going to be 0. And there's one more way we can see where derivatives are going to be large and where they are going to be small. What we do is we pick this starting point and this final point and we join them. We make a slope actually, and then we look for the angles with the x-axis, alpha, and you do the same here and you connect them, maybe beta, and alpha is larger than beta, and so you look where the slopes are steeper, and right here the slope is steeper compared to this one, right? And so derivatives are going to be larger around those points. And what is the slope here? Well, it's flat slope, and so there is no the changes, there's no changes actually, and so derivatives around those points, of course, are going to be 0. And so right here the gamma is 0, the angle is 0. So that's how you can see where the derivatives are going to be larger and where they are going to be small. We call these slopes between 2 points average slopes, but derivatives are about instantaneous slope. They want to know the slope at one point, or maybe I should say slope around a point. That makes most of the sense. And so how am I going to find you an instantaneous slope? Well, we use our average slope and we do something with that to get you the instantaneous slope. And to do that and show you that how it's done mathematically, I need a new function. Let me clean it a little. A new mountain, a new function. And so this is your new mountain. That's x, that's y of x, and the mountain goes something like that. Suppose I want to find the derivative at this point, the instantaneous slope right there. To do that, I'm going to make a side step, a large one, delta x, and you would find yourself somewhere here. So before I can find your instantaneous slope, I'm going to look at the average slope. And so average slope between those 2 points is delta y over delta x. Well, delta y is the height difference between this height and this height. So height at point, oh by the way, if you call this point x, then this point will be x plus delta x. And so height at x plus delta x minus this height, the height at x, right? You subtract this by this, you get this. That's your delta y. And you divide it by the side step that you have made. And so this is the average slope. And this is going to look like something like that. And now I'm ready to give you an instantaneous slope. What I am going to do is, I'm going to pull a trick. I'm going to make this side step shorter. You will see why I do that in a moment. So your final point is no longer there, it's right here. And now the slope between these 2 points is going to look like so. That's the average slope. And you may be like, how is it helping? Come on. Well, you are in for a surprise. I'm going to make this side step even shorter. So you are here. Even shorter. So you are here. And then this will be your slope between that. And I hope you can already guess it, what I am intending to do. I'm going to make this side step so small that these 2 points come too close that you consider those 2 points to be just one, right? Because they are too close. And so let me make you a side step of very short. And so this point is going to be somewhere around that point, almost near to that. And now you connect them. So this is your now the new slope. And since these 2 points, this side step is too small, these 2 points are just one. And that's the trick. I have found you a slope at one point. And they call it instantaneous slope. What we've been doing is, this was the average slope, and then we were making delta x shorter and shorter, so this slope was moving around, and now this slope becomes tangent to that curve. And this gives you the derivative at that point. It tells you how fast you are climbing. Oh, you are coming down. How fast you are coming down as you move in the x direction. And so what we've been doing is mathematically that we let delta x to approach 0. And then this average slope, we give it a new notation. We say dy dx. So your delta x changes to, not delta changes to d as your delta x approaches 0. So this gives you your instantaneous slope at this point. And nothing is so special about this point. You could have done it here, that's your starting point. You make a side step, delta x. Then you will climb up by a height of delta y, so you are here. And now you are going to make this delta x shorter and shorter, then this point will come almost on the top of that one. And so you are right here. And now again, what you're going to see is your average slope that was between these 2 points becomes the instantaneous slope when you let to delta x to approach 0, and then that becomes the tangent to that line, tangent to that curve. And you could have done the same for this point. Right here it would look like that. And you can see the slope here is steeper than there. So derivatives around those points would be larger. Here they will be small. Again they will be larger, but with the negative sign, because you know this is the angle, maybe I should call it psi, it is going to be negative, right? This one tells you how fast you are going down, and this one tells you how fast you are climbing up. That's the difference. That's what negative sign tells you, that you are going down. That's what it all tells you. Alright, I think I am done with mountains. Now I want to have a different example. A car moving on a road. Suppose a car starts from the rest, speeds up, then you push on the brakes because you see the red light ahead of you. You have to stop, right? And let me clean it up. Oh, it looks horrible, but I think this is best. I can wipe it up. And so let me give you the car's behavior as a function of time, right? So give me a moment. I need it for velocity too. So this is your car's behavior as a function of time, and this is the road where the car is moving, x of t maybe, and the behavior is something like so. And let me give you some, and this may be in seconds, 1, 2, maybe 3, 4, look, between 3 and 4 you are going to cover most of the distances. If you compare it with one between 1 and 2, look, this is the distance you are going to cover between 1 and 2, and this is the distance you are going to cover between 3 and 4, maybe in seconds. And so right here, not here, your car is never here, the car is always moving around here, but it is moving faster somewhere here, right? And so let me show you. I actually, my mom brought me a car, so that's how it's moving. It starts slowly, then it goes fast, then stops at red light. So red light is somewhere here, right? And you can also see between 5 and 6. So right here you are slowing down, and here between right around those moments or points on the road you are going faster. And you look for the slopes, right here. Look, the tangent line, the slope, is going to be steeper if you compare it with this point in time at this moment. Look at that. So the slope is steeper here than there, and you can also compare it with that again. So this tells you how fast your car is moving along the way. And calculus is about a connection between two functions, the function x of t and its velocity. And if I compare it with that, if I draw you velocity as a function of time, which is really dx dt, and that's your velocity as a function of time, I can draw it, because around between 3 and 4 you're going to have the largest velocity, right? You're going to have largest velocity, and right somewhere here around 2s you're going to have a little, maybe around here, and you could do for maybe this point. Oh, look, this slope and this slope almost looks like the same. So at this time at 5 they have the same value. And then right here, here's the red light, and so right there you are at a halt. And so again, because you started at from rest, and so this should look like somewhat like that. So this is a function, and this is its derivative. Derivative tells you how fast the distances are changing. It tells you how fast, it tells you the velocity of that car moving on the road. And so right at that moment you have the largest velocity, and here you have a lower velocity. And right here, when you started and at the red light you had 0 velocity. Remember, your car is always here, it's moving here, because it is x and t graph. I can give you another function, not another function, but a different kind of graph with a car. Again, car's behavior as a function of time, and this might look like that. And you're going to struggle with that, and you will see that the derivatives, because right here the slope is going to be flat, right? So you might expect velocity at that point. It's like you are already going with a lot of speed, and somewhere here there's a kid playing around on the road, and so you have to push on the brakes, right? You have to stop here, and then you again speeds up. Look, at around these points you have most of the velocity. Your speed is the largest. You're going faster, and so its derivative. If you plot, if you look for the values of these slopes and you plot it on the dx dt as a function of time, it should look something like that, and you deal with that. So this was the example, and that's your problem. You do that. And now I'm going to move to mathematics, a little bit of that actually. So we had equation, the average slope, and then we approached delta x to 0, and then we got, let me rewrite it here, dy, let me, because yes, dy dx, it was, let me just write it, minus y at x divided by delta x, and then we did delta x approaches 0. And now I am going to take an example, and it's again a car moving on the road, and now this time this function is t squared. So this is a parabola actually. So this is, it should look like what it should look like, right? And I want to find now the derivatives, right? I want to find here, here, there, and I mean I want to find the derivatives, because your car is moving again here. Even I am confused sometimes. I think it's there, it's never there. So I want to find the velocity here at this moment, here, here, and there. And I will start with that equation. First, you wait for a while. So that's your delta t, and then you compare it, how far you have gone. So that's your delta x, right? I will use that equation. So let's start that. So dy over d, oh, it's not dy dx now. Remember, this is a function of dx dt. This is a function of time. So what you do is, so they actually write limit. So this notation that I've been writing as this, they write it like that. Just a fancy notation, nothing is special about that. And so function's value at point t plus delta t, what is it? Well, it is t plus delta t squared, right? So it is t plus delta t squared minus the function's value at t. So this is your point t. What is it? It is t squared, right? Look at that. Divided by delta t. Well, this is a plus b squared. You can open it. Let me see. Yes. So let me do it here. dx dt. It is going to be limit delta t approaches 0. It is t squared plus 2t delta t plus delta t squared minus t squared divided by delta t. Look, t squared minus t squared, they go away, and there's a delta t here, and there's a downstairs delta, so these also cancel once you have removed them, and there's a delta t squared, and then downstairs there will be delta t. And so what you are going to see, this equation finally becomes with limit, should I write it? Oh, forget about it. All I'm doing this one here. So this is 2t plus delta t, right? And now we can substitute for delta t to approach 0. So this becomes, you can neglect it because delta t is almost 0, and so your dx dt is finally 2t. So that's the derivative of t squared, that's 2t. And if you want to find the speed at point, maybe let's say this t was 2, maybe 2 seconds, then derivative's value dx dt at point 2, not at point 2, at time t, which is 2 seconds later, it is 4, right? So derivative at time 2 is 4, so this slope's value is 4. So this is dy, not dy, have I been known, it is dx dt at point, at time 2 seconds. And now you could do the same if you had a function with x of t of t cubed, and the function for t cubed looks like this, something like that. And you could do the same for this one, but instead of, so what do you have to change here? You have to change it to 3 and this 3, and you open for this one a plus b cubed, and then you have to expand it like that. What do you do? And I'm going to give you the answer. So d cubed, so dt, it is going to be 2, not 2, it is going to be 3t squared. And remember, when we take the derivative of t squared, it was 2t, and you may call it 1. And if you do it for d t to the 4, you will find it to be, its derivative will be 4 times t cubed. Right. And now I hope you can see the pattern. When you take the derivative of t squared, 2 comes down and you are left with 1. And the same goes here. T3 comes down, 3 comes down, and you lose 1, so you are 2. So I hope you can see the pattern. So if you, I will do it here. If you take the derivative of t to the n, and where n could be 1, maybe 0, 3, 4, and goes on, it would look like, since look, 3 is coming down, so n will come down somewhere here, and t, and then you lose 1 from 3, so it should be n minus 1. Right? Yes. Should I rewrite it here, because everything has mixed up? So derivative for t to the n is n times t to the n minus 1, and that's the important equation in calculus. That's the derivative for any polynomial with power n. And you can do the pattern here. Let me remove some of that. That's all. Excuse me, for my blackboard is so little, so I don't have really space. And so d derivative of t, you can now complete the pattern, right? So it should be 1t to the power 0, right? Look, here you have 1, 2, 3, 4, and then look, here you have 0, 1, 2, 3. and so it is really 1, and that's the very important derivative in mathematics. That's a derivative for any polynomial function.